Yeah. So morning we are discussing the uh, design considerations in the sand casting, that is casting components, and we discussed the different considerations what we supposed to make while you are casting, while you are designing the components which needs to be casted, right? So now let us continue with the some more aspects. So morning we discussed only few of the topics. That is what we call it as the shrinkage, potting line, draft, and rises. I think we stopped at this point in the morning. So let us continue now. So here, the next important thing, what the design considerations while you are doing the casting is the risers, the placement of risers. So usually the risers are generally attached to the heaviest section. Heavier sections are closer to the riser and thinnest sections are furthest from the riser due to the faster solidification in thinner section. This minimizes the chances of getting voids. So this is what I was just stopped at the last class or morning class. So where actually the risers needs to be placed. See, the one of the most important aspect in design regarding the placement of risers in the case of a casting components. So because the when you start pouring a molten metal, right? See, the molten metal will start flowing across the mold cavity, and wherever you have the sections or which are very thin, so they will start solidifying. Okay, so the sections which are at which are having thicker, so they will take some time to get solidified. So this difference in the time of the rate of solidification will always results in voids. So therefore, what they generally do is the risers will be always been kept across the attached to the heavier section, and the risers are very close to the heavier sections, and the thin sections are very far away from the risers, so that the time taken for the material to flow to the thin sections will more than compared to that of the time taken for the material to flow to the thicker sections. So this is a very important thing. So being a design engineer, you should specify where actually the risers should be located or should be placed. So for that, you have to use the consideration that if you find any thicker sections, so across that are heavier sections, so across that section, the riser should be placed, and the thinner should be almost further away from the risers. This is what you supposed to be designed for the casting, right? Next thing is the ribs and webs. See, very important thing here. So when you have any component which are having a ribs and webs, so in this case of the case of heavier section, a rib intersection with the casting wall can cause hot spot shrinks. This is a most important casting defect, what we can call it as hot spot shrinks. So the intersection of the ribs across the heavier sections always results in the hot shot springs or hot spot shrinks. The number of intersecting ribs should be minimized to avoid the hot spot shrinks in the sense. So you should think of there should not be any more number of the intersecting ribs. Okay, whenever it is necessary to bring all the ribs into a single point, a cored hole would help in faster solidification, therefore thereby avoiding the hotspot shrinks. So please be careful while you are designing the components. So try to avoid these ribs and webs. So because both will going to contribute for the welding defects called hotspot shrinks. So hotspot shrinks in the sense the shrinkage will be more and you will going to get a defect in the casting. So this is what ribs and webs. So look at here, this is the one some of the diagrams what they have shown over here. So this kind of things you need to improve. It is very poor design because webs are there. Look at the webs, ribs, and this is slightly improved, and this is also more slightly improved. So better. So these are all better things. And see here. So how it is should be. See, it should be poor, better, and best. See, this is a very important thing while you are designing the casting components. So take care of ribs and webs. So there should not be more number of ribs and webs. And if you find all the ribs come together, better make a core, whole hole. See, look at this. So how they have done. So instead of having the sections like this, okay, this will going to get the hotspot strings over here. This also, it is very poor. This is okay. So make like this. If you want more number of ribs will come into the picture, they will going to join. So at the cross section, they make it as a hole and leave it. So cored holes, we can call it as a cored holes. So this is a very best way of designing the components for casting consideration, casting purposes. Next comes corners and angles. The hotspot are most common defect in corners and angles of casting design. Hotspots. So some of the spots might not be get solidified. So they will remains hot. So that is because of the casting defect. Okay. Use rounded corners having same radius for both internal and external corner. Again, too much rounding promote shrink defect in the corner. In the sense, better to use both internal and external corner having the same radius. So whenever you find any pods or any features, so which needs corners and angles. Okay, so better the corner should be rounded. It should not be just like an angle. It should be rounded, and that radius of that round, or what we call it as a fillet, of both internal and external corner should be same. Again, too much rounding promote shrink defect in the corner again. So that radius for the corner should be optimum. You cannot make more radius or more rounding. More rounding will also results in the shrink defect. Okay, especially in case of T sections. Look at that in particular. In case of T section, larger inside radius can be used to minimize stress concentration and hotspots. So you might be getting a sections different T section, I section, L section, C section, like that, different where you will going to find these corners. Okay, so in this case, sorry,
to find the centroid of the L section.
Hello.
Sir.
Yes.
Sir, mechanics of solid centroid, to find the centroid of L section and I section.
Sorry, I didn't get it, Harsha.
Sir, I section, L section, we are using for find the centroid and moment of inertia and B.
Yeah. Same thing only I'm talking about. Those kind of sections, when you have to make a casting having those kind of sections, okay, in such cases you may find it's difficult. The corners also, it's very difficult for you to get that one. So in such cases, the radius should be increased. That's what they're saying. The larger inside radius can be used to minimize stress concentration and hotspots. So in the sense, whenever you find at T sections, okay, the inside radius should be very large. This inside radius will always minimize the stress concentration as well as the hotspots. Okay. Use of dished contours, one on each side of the center legs, are also effective. This is what they say. Use of dished contours. I think we will see in the next diagram over here. So look at these diagrams over here. So please understand these diagrams. This is very important. So what are the changes? Which one should be avoided and which one should be required? So please check it out, because very important diagrams what we are showing over here. Okay, so here, see, this is the hotspot because of getting rapid cooled. This is very poor. This is better. Hmm. So this is the corner angles should be, you need to have more radius, larger radius. Okay, so when you are designing any component, okay, be careful with while you are giving the corner angles or corner radius. The inner radius should be as large as possible, so that you can prevent, see, this kind of hotspot you can just uh, minimize. See here also. So instead of having a sharp corners over here, okay, so if you give a radius, see, look at this. This is where you have to prevent the sharp corners as much as possible. Hmm? Okay, so there are some of the uh, ways in which you can corner and angles can be minimized. The next thing is the wall thickness. If the metal is flowing for a longer distance in the mold, then the section should be heavier. But heavier section also cause problem with the voids and porosity. Keep the wall thickness as uniform as possible. Okay, so in the sense, what they're saying is, if the metal is flowing for over a period of time, so we will think that the section will become heavier. But heavier sections will also cause the problems with voids and porosity. This is a very important, this is a very major problem with the castings, what you will going to get it. So heavier section will also cause problems with voids and porosity. Keep the wall thickness as uniform as possible. In the sense, the wall thickness across each and every casting component should be uniform. So therefore, please keep the wall thickness as uniform as possible. See, look at here, it is original design, internal porous area. So now this is the preferred design. The changes you can notice over here, how they have made the changes. Any other thing is there? No, not so what only thing. So they have maintained the wall thickness uniform everywhere. So see, wall thickness. So this is not the porous one. So this is internal porous here. So here they have maintained this wall thickness uniform everywhere. Okay, see here wall thicknesses are so different here. So they have made everything same. The next important thing is section changes. See, abrupt changes in the section must be avoided. In the sense, so I think this you might have been studied, being a machine design students, you might be knowing why that abrupt changes in the sections needs to be avoided. So what happens? Abrupt changes in the section happens. Anybody?
Stress concentration.
Yes. Whenever you find any changes in the abrupt changes in the stress, abrupt change in the sections will happens. So the what we call it as the localized stresses will be more. So that will leads to the stress concentration. So therefore, so being a design engineer, you supposed to know how we can avoid these abrupt changes in the sections. So because that will leads to the stress concentration, and ultimately the component or a part may fail because of the stress concentration. So therefore, so in the case of components which are having changes in their section, their relative thickness of the adjoining section should be less than 2:1. So if this is 2, and next should be less than 1. So it should not be less than 2:1. If the heavy section is unavoidable, then a taper of 4:1 is advisable. So look at this is the heavy sections over here. Okay, see this is bad and this is good. Look at here how it will go. The taper what they're going to give 2:1 taper. See this is the bad design and this is the good design. And here also, see look at here, this is the bad design and this is the good design. Look at here how you have to change or how you need to modify your designs. Okay, so and here also, see here how they have changed it. So these are all the way you're supposed to see. This is bad. What they give less than, greater than, less than or equal to 2. So they are given. So how they can change this, the sections, the abrupt changes in the sections. This has always been the way you're supposed to design the components. Yeah. Next thing is interior wall and sections. Yeah, these members should be 20% thinner than the outside members since they cool more slowly. Interior walls and sections. So these members should be 20% thinner. The interior wall and section should be 20% thinner than the outside members. The main reason for that is the interior walls, they cool very slowly. So the solidification, when the components start solidifying, the time taken for the interior walls or inner walls to get cooled will be very more. It requires more time. So therefore, that should be 20% thinner. You have to make those walls 20% thinner compared to that of the outside members. Next, lightener holes. To reduce the weight in a low stress area, lightener holes can be used. So because whenever you find uh, the weight of the casting is more, uh, and to reduce that weight in the low stress areas, lightener holes can be added also. And holes and pockets, the draft on the inside of a pocket must be twice as on the surrounding outside surface. The depth of the hole or a pocket should be not more than 1.5 times its narrowest dimension if it is in the drag half of the mold, and this depth should be not more than the narrowest dimension if the hole or a pocket is in the cope half of the mold. So holes and pockets. So when you have any pockets or any oil holes or whatever it might be, okay, or sometimes you will going to get the through holes sometimes. So all these things, see, inside the pocket must be, draft of an inside of a pocket must be twice as the surrounding outside the surface. The depth of the hole should not be more than 1.5 times its narrowest dimension. This is a very important thing. So the depth of the pocket should not be more than 1.5 times its narrowest dimension. This is very important if it is in the drag half of the mold. So if the pocket you are finding in the drag, so the depth of the pocket should not be more than 1.5 times its narrowest dimension. If it is in the cove, okay, the depth of the pocket should not be more than the narrowest dimension. So here In the drag, it is 1.5 times, but in the cope, it should not be more than, it should be always less than the narrowest dimension you're supposed to take care of. This is what I was talking about. See, cast hole, simple drill dimple over here. So not this. This is a little bit improved, and this is the best. So look at here how they have been chamfered over here. It's not exactly straight. Next, bosses and pads bosses. Pads and lugs should be minimized as it creates voids and pores. So 5 to 10 occur over here. So make it like this or this. Bosses and pads. So when you have a pads, so better don't avoid this kind of things. Pads. Better use this like the lugs or pads. You should be having this kind of geometry. Okay, because the pads will going to create the voids and hotspots. Next comes cores. Cores is recommended to avoid. It is recommended to avoid the use of cores as it is expensive to make and handle. So the cores basically they are used whenever we require any what we call it as the intricate shapes in the casting. Am I right? So especially when you have a hole, when you want to make a hole feature in a component, so we generally go for a course. But these cores are not advisable. They're not recommended to use because these cores are relatively expensive. So they are very easy. They're expensive to make and very expensive to handle also. Okay, often use of cores are unavoidable and are used to make holes. That's it, right? In such cases, the core diameter should have at least equal to the surrounding wall thickness and preferable twice the wall thickness or more. If possible, side bosses and undercuts should be avoided. So whenever you are making or whenever you are using a hole or a core, the diameter of the core should have at least equal to the surrounding wall thickness. So the through the feature where you will going to get the cores or to get the hole, the wall thickness, the core diameter should be at least equal to the surrounding wall thickness, and preferable is it should be twice the wall thickness and more. If it is more than twice the wall thickness and more, then it is preferable. What's they say? In case internal cores are used, addition of venting holes are required for removing the gases that are generated while core comes in contact with the molten metal. So when the internal cores are using, where addition of venting hole is required. So when you use internal cores, so you need to make the holes, the venting holes. The purpose of making venting holes is removing gases that are generated while the cores comes in contact with the molten metal. So when you pour a molten metal, the core will also comes in contact with the molten metal, and there is a possibility of the gases evolving, and these gases should come out of the mold cavity or from the casting pot. So to obtain that, so venting holes can be provided. So venting holes will prevent the gases to just get settled within the cavity itself. So therefore, once you have a venting holes, all these gases will comes out of this, and it will make the casting more quality, right? So this is what we say: core 1, core 2, core 3. It is totally expensive. One core less expensive. Again, one core less expensive. So no core much cheaper. No core, much cheaper. This is what the people say, how we can get the things done without using. See, minimize the need for cores as much as possible by eliminating undercuts. See, undercuts are there. Please minimize these undercuts. So when you minimize undercuts, directly we can use without using a core. We can cast the component. Yeah, another one. Avoid small core holes. So internal pockets in casting to facilitate cleaning after casting. See, look at here. Minimize core hole size. Better core hole size. D is equal to 2T. So this is the wall thickness. Here it is D is equal to T. And here we have made T is equal to 2T. In the sense, we have to minimize using or avoid using small core holes. And internal pockets in casting to facilitate cleaning after casting. This is the incorrect way and this is the correct way. Yeah. Next comes gears, pulleys and wheels. To minimize the stress, proper balance between the section, size of the rim, spokes and hub must be attempted. It is recommended to have odd number of spokes with curved in shape. Excessive surface variation is to be avoided. See, whenever you are making as gears or pulleys or wheels, it requires a spokes, right? So to minimize the stress, proper balance between the section, sizes of the rim, spokes and hub must be attempted. So generally, so the main purpose of providing spokes is to provide a proper balance between the sections. So therefore, so generally they will have a rim, they will have a spokes, they will have a hub. And generally what they recommend is to have odd number of spokes. Don't use even number. Make it odd number of spokes with curved shape. With curved shape. That is the one which has been preferred in the design of pulleys or wheels. In a sense, if you look at this straight line, the straight spokes are not required. They want these curved spokes. And the number of curved spokes should be odd number. It should not be even number. Next comes lettering and other data. Any lettering should be parallel to the potting line. These data need to be placed in such a way that this will not interfere with the machining. This can be either sunken or raised above the surface. Since when you want to type, if you want to write something or if you want to specify something on the molding or casting, so it needs to be either sunken or it might be raised. Sunken in the sense it needs to be embossed. Otherwise, sunken means it needs to be pressed, and embossed means it is just like a raised. So here, what happens whenever you want to provide any data or lettering across the surface of the casting components, right? So these letters should be always parallel to the potting line. Okay, and also the data needs to be placed in such a way that these will not interfere with the machining, because you will go into machine the casting after you just complete your machining, after you are giving for the machining surface, right? So here the letter should be always placed parallel to the potting line, and you should take care of that. These data should not come parallel to the surface which will go into undergo a machining. So that's why they say these should be either sunken or raised above the surface. Okay. Next thing is weight reduction. Casting weight is minimized by removing metal from low stress region and adding to the high stress area by the use of simple, inexpensive pattern change. So, how the weight can be reduced? Weight can be reduced by removing the metal from the low stress region. You remove the material from the low stress region, you add to the high stress region, okay, and we will make use of the simple, inexpensive pattern changes. And the next thing is insert of different metals. It is sometimes desirable in casting to incorporate a section of different material, either harder or softer than the base metal, depending on the purpose and is proved to be economical. So in the sense, the you may need to have the different materials to be inserted within the casting. So which might be having a either harder or softer than the base metal, and that depends upon what type of purpose and you are using it for, and of course it proves to be economical. So this is the casting inserts, what we can say here. Cast iron wear surface insert in an aluminum aircraft brake lining, brake casting. So how you can insert the material within one material. This is what the different materials, right? So this is what the different guidelines, the design considerations in casting. So please remember everything. So because very important from the examination point of view, right? So this is just a guidelines or the considerations that needs to be taken while you are designing the casting components. Okay. So in the next class, I will talk about some more concepts regarding the pattern and what we call it as different types of pattern, along with the mold box as well as the potting lines. So how you can identify the potting line with the probable and possible potting lines, how we can distinguish, and what is the necessity of a core, and how we can avoid cores, whether it is a drilled core or whether it is a machine core or whether it is a sand core. Like that, there are plenty of things are there. Okay, those things I will going to discuss in next week's class, next Monday class. Okay, for time being, I will just stop the class. So if you have any clarification, you can. Otherwise, you can go to the Google Classroom for attending the quiz. I will upload the quiz in your Google Classroom. Yeah, the quiz is assigned. So you can start attending the quiz over there.
Ada kelasnya.